Good afternoon, it's just Schweitzer. We're going to run through a little video here on what happens when you mix an acid and a base. Now again, this does depend on what you're actually mixing. So we're going to go through two different scenarios. Now keep in mind that when you add a strong acid, let's say for example HCl, you're not actually adding HCl. You're adding H plus ions and and chloride ions. The chloride ions will do nothing, and the H plus ions are really the most potent version of any acid. If you're adding NaOH, you're really adding Na plus ions and OH negative ions. So one thing to kind of keep in mind is that when you add H plus ions, these guys, and hydroxide ions, these guys will always react very strongly with whatever you add them to. These chemicals will go to completion and will react until there is a limiting reactant. Treat these individuals like any typical stoichiometry problem. We're going to spend the first couple slides just looking at these. We have a couple different versions of that. Okay. The first version would be, let's just kind of highlight these quickly here, and you'll see them come up again. We could do H plus OH minus, just yielding water. Okay, now I'm leaving the spectators out. That would be like HCl plus NaOH. Or you could do like H plus, which is HCl. Okay, HCl. Plus a weak, which would be like NH3. And in this case, the acid would just protonate this guy completely until something ran out, like a stoichiometry problem. And then that would form NH4+. The other version would be the base version of this, where you have like a base reacting with NH4+. This would react with one of the hydrogens on there and produce water and NH3. Either way, if you have one of these guys, these guys will react until either they're gone or the thing they're reacting is gone. That's a standard stoichiometry limiting reactant idea. Now, the other option would be if we only have weak components. We don't have one of these guys. All right, we just have HX and X negative. These guys only run in hydrolysis reactions. So we could have two different versions of that. We have HX plus H2O yields H3O plus X negative. Initial stoichiometric ratio end. And you simply plug in the amounts that you have. This guy here and this guy right here, me run a typical mathematics solving for my ending concentrations. And then, of course, we have the other version, which would be the X negative version. And that's just going to be, I'll put this right here, which would be X negative plus H2O yields H3O plus. That's going to be OH negative, sorry. There we go. OH negative plus HX. And once again, initial stoichiometric ratio end. Now, on this particular scenario, this guy right here, put a smiley face here, will be the same concentration as this guy right here. And this guy here would be the same as this guy's here. If you have both of these guys present, this guy and this guy, then you can use either reaction you want and it's not going to matter. If you only have one of them, then if you only have the acid, you have to use the acid equation, which would make this guy 0. If you only have the base, then you have that guy, then making this guy 0, then you have to use the base version. If you have both, then you can use either one you want. Okay. Now the mathematics we're doing here is sort of the preliminary stuff for what's called a titration. This is just the mathematics behind a titration. So we'll walk through a couple examples of these, and if you're familiar with titrations, you'd be like, oh yeah, that's kind of the math behind it. But all we're going to do now is basically highlight a couple of examples of each of these types of scenarios. There's not going to be a ton of problems. So we're just going to go through one or two types, and then for the most part, they don't change at all. So you need just to go to the workbook and try a few problems on your own. Our first example, okay, is HCl plus NaOH. So this is going to produce a salt and water, acid base, salt and water. So it's going to be H2O. What's with the salt there? See, it's above it. NaCl plus H2O. Some people will call this HOH, and that's fine. Ionic. So we're going to split things apart when they need to be split apart. That's H plus Cl minus. A strong is always drawn apart because they aren't really together. Plus Na plus OH negative. This thing is actually aqueous. It's not actually together. So Na plus Cl minus. And the water is liquid and it is actually together. H2O. Net ionic. Let's eliminate spectators. That's this guy and this guy. So it's going to be H plus OH negative yields H2O. Like I said, this is just going to run until something runs out, and the spectators are not involved in anything. You could write out a little ice table on this guy and count how many you have here, and then count how many you have here, and you could fill the whole table out, and that will, the ending will tell you what you put over here. But I'm going to do it this way. I got 1H plus and 1 hydroxide forms water. And then 1 hydroxide and 1H plus forms water. 1 hydroxide and 1H plus forms water. And it looks like these two guys are in what we call equivalence, meaning the same quantity of each. And then, of course, the spectator of chlorides, I'm just going to call them negatives over here. And the spectators of the nitrate sodiums, I'm just going to call positives. Okay. All right. Let's try an example of this. 10 milliliters of a 0.1 molar NaOH reacts with 0.05 molar HCl to equivalence. So the equivalence means the moles, okay, are equal. Okay. So in this case, the reaction is NaOH plus HCl yields, and it's going to be equal. The product, of course, is NaCl plus water, and it reacts in a 1-to-1 ratio. So if the moles are equal, all right, so I have 10 milliliters and I have 0.01. A long way of doing this would be to take your molarity formula and solve for moles. Molarity times liters equals moles. And of course, if the molarity is 0.05, 0.1, this is 10, and it takes, I have 0.05, the estimating way to solve this problem would be to say, okay, I have half the concentration is over here, reacting at 1-to-1, therefore I'm going to need 2 times the volume. My volume will be 20 milliliters. The long way to do it would be to literally write out a whole chemical equation, which would be, I'll give myself some room here, NaOH plus HCl yields NaCl plus H2. And I'm thinking that if you ever see a problem like this, they're not going to want you to do the long way, they want you to do the short way. So they're going to give you some nice easy numbers that you can just do like this. But what you would do here is you'd find the moles of each. So it's going to be 0.1 equals X over 0.01 liters. And that's 0.001. And this is and it wants to react them in equal amounts. So I guess you don't even need this. I just want the same number of moles of this guy to be 0.001. So I'm going to use molarity equals moles per liter. The concentration is 0.05. And I want the moles to be 0.001. And then you solve for this. And of course divide out. And X should equal 0.02 liters or 20 milliliters. 10 milliliters of 0.2 molar HCl reacts with 20 milliliters, not 10.2, 20 milliliters of NaOH, causing us to have a pH of 7. Now, because we have strong acids, that means the conjugate, as we learned in the salts video, the conjugates are neutral. In this case, my salt is neutral. Only product I have is neutral. So the equivalence does in fact occur when the pH of 7. But this is kind of a rare instance. My products aren't always neutral. So be aware that the equivalence point does not always equal 0. No. Alright, so that only happens when you have a strong acid versus a strong base. Alright, so what is the concentration of NaOH? Okay, so I got this guy here, we're reacting to equivalency, and because I have twice the volume, this thing must have been 1/2 the concentration. You can use the same method you have here, and therefore it must have been 0.1 moles per liter. That's where we'll leave that problem. Twice the volume, half the concentration. So mind you, if something has, pretty common little phrase here, equal molarity of equal volume. What does that mean? Well, it means molarity equals moles per liter. Molarity times liters equals moles. If this is the same between two items and this is the same between two items, then the moles are the same. Alright, let's jump over to our next option here. Now I have a weak and a strong. Okay, so now how do we write this? Well, however you think about it, but it is up to you. But the OH essentially is going to grab onto the HF. Or you could think of it as the OH reacts with the H+, from which this thing gets through hydrolysis. But usually people just think of it as this guy reacting with that. So it's going to be NaF plus H2O, HOH. Ionic wise, okay. Now this being weak is together. HF plus ONA plus OH negative. Separate those because they're strongs. Very soluble. Produces. Now this is actually together. So it's Na plus F negative plus H2O. Eliminate spectators. The only spectator we have here is the Na. The F actually changes a little bit. So the ionic is going to be HF plus OH negative yields N F negative. Alright, that's that there. Plus H2O. Alright, so once again we have this guy here. And I have them set up at equivalency here. So this guy reacts with this guy to produce a water and an F negative. This guy reacts with this guy to produce a water and an F negative. This guy reacts with this guy to produce a water and an F negative. And of course, these are just my spectators. 1, 2, 3. And that's it. Okay. Alright, so how much 0.1 molar NaOH is required to neutralize 10 milliliters of 0.05 molar HF? Now you'll notice here on the previous one that regardless of whether they're strong or weak, one HF still can neutralize 1 OH. And this is really important. Things don't react based on strength. They react based on numbers. The moles of these guys. So with that being said, the quantity matters, not whether this one's strong or this one's weak or this one's strong. So keep that in mind. So how much 0.1 molar NaOH required to neutralize 10 milliliters of this guy? Well, whatever moles we have here is the moles we need here. And that's kind of how I did it the long way the first time. So let's just do that again. 0.05 equals 0.01 liters over x moles. And we'll multiply it out, this times that. So 0.01 times 0.05 is 0.0005. So x equals 0.0005 moles. And of course I have that concentration. So what volume would I require to get this number of moles with that concentration? So it's going to be molarity equals moles per liter. This is 0.1 equals 0.0005, solve the moles. Divide them out, and you're going to get, in this case, well, you divide it out, you're going to get 0.005, just drops down by 1 percentage, x, or 1/10. So 0.005, which of course is 5 milliliters. Now think about this without all the math. This guy here is half as concentrated as this one. Or you can say this is 2 times as concentrated, so it's going to need 1/2 the volume. This is 10, so this only needs 5. That's the better way to do it. This is going to show up on like a multiple choice style question, where they're just going to want you to do this math proportionally. How much 10 milliliters of 0.1 molar HF reacts with 15 milliliters of NaOH? The reaction is an equivalence. Okay, so 10 and 15. So what's the what is the concentration of NaOH? Okay, so the moles are equal. So let's just take a moment here. 0.1 equals x moles over 0.01 liters. That means my moles equals 0.001 moles. And then just take that divided by my new volume, 0.015 liters. And let's see what we got. We got 0.001 divided by 0.015 equals about 1/10 of 2/3, if you want to call it that. So 0.0667 molarity. Okay. So what is the concentration? That's that guy. Is the reaction neutral, acidic, or basic at the end? So all we're doing is producing, well, let's draw a picture of it. They're equivalents, so we have some HF. It's HF plus NaOH, and we're producing NaF plus water. So if we draw a picture of this, we would just have water molecules, F negative molecules, and Na plus molecules. I don't know how many we'd have, but that would be what we have, so a multiple of that. And this guy obviously is neutral. This guy here is the conjugate of a strong, which makes it neutral. But this is the conjugate of a weak. This is a weak acid, so this is a weak base, and therefore this solution is basic. Okay, and therefore it is basic at equivalence. Okay, so now we've covered the main parts of mixing strongs with other things. Always having hydroxide or H plus present. What if we do it where we don't have that, just mixing weaks together? This particular problem wants us to just start out by going through the old math. What do we do if we just have one of these guys? Okay, NH3 only. Well, it's going to be, I'm going to skip all the mathematics. Well, let's do a quick one first here. NH3 plus H2O yields NH4 plus OH negative. Initial stoichiometric ratio N. This is 0.1, not playing a role. Minus x, 0, 0, plus x, 0.1 minus x, x, and x. Now none of this would be considered work on an AP test. Absolutely just for you. So it's going to be KB equals, all right, and then it's going to be these two products, x times x over 0.1 minus x. I'm going to use a shortcut rule here. So it's 1.8 e to the negative fifth equals x squared over 0.1. Multiply out square root, and then this is going to give us our POH. So 1.8 e to the negative fifth times 0.1 equals square root, produce the answer, is 0.00134. So x equals 0.00134. You can negative log this guy to get the this guy to get the POH. 14 minus that guy will give you the pH. So we'll negative log this thing. Make sure you show your work on all these things. Gives you 2.87. If you're plugging your calculator, show what you're doing. And so this is going to be this negative log of this guy is equal to 2.87. And then 14 minus this guy equals 11.1. Equals 11.1, and that is my pH. Very basic because this is all I got. Okay, well this guy. Alright, let's give ourselves a little wall here. Now I'm going to go skip all this and just go 5.6 e to the negative 10th equals x squared over 0.1. Multiply it out, I get 5.6 e to the negative 9th, negative 11th, and square root it. So okay, so my x at this point equals 7.48 e to the negative, and it's going to be 1, 2, 3, 4, 5, 6, I believe, if I counted correctly, e to the negative 6th moles per liter. So now we're going to take the negative log of this value will give me my pH, which equals, log of that, 5.1. Okay. Once again, it is going to be acidic because we only have the acid. It's not a very strong acid. This base is the conjugate of this guy. They're conjugates, much stronger than that guy is. Power of 5 stronger. Okay. So let's move along here. Next question. What is the pH of a solution, acidic, basic, neutral, of when this is mixed with this? And I'm assuming we're going to be mixing the same volumes, equal volumes, because it matters in this case. We have, in this case, because of the Ka's we just had here, okay, these two would be mixed, and so they would run out. Okay, we'd have the desired reaction NH3 plus water, so produces NH4 plus OH negative. This guy is driving this way to produce H plus ions. This guy is driving this way to produce OH negative ions. And because they're equal concentrations, there's the concentrations of equal volumes, okay, and because this guy has a larger KB, you saw that in the previous slide, this guy wins, and the reaction will be basic, hands down. So this guy here, how would we draw this? There's no way really to draw this. We just really would go NH3. There's 3 of them. We wouldn't even lose any. It just would be kind of a weird question. NH4 plus, NH4 plus, NH4 plus. And anions, 3 of them, and that's it. You wouldn't even draw anything else. I mean, if you really got down to it and they forced you to draw something, you could draw a hydroxide, yes. But there's also H pluses present too. It's just more hydroxides, slightly more hydroxides because of this guy's driving us this way. So, I'm sure we'll have a calculation version here. There's the answer to that. And here we go. Let's actually calculate out this. I'm going to add a little dealio here. Let's say a page. Okay, what if we have 10 milliliters of NH4Cl react of 0.1 molar reacting with 10 milliliters of 0.1 molar NH3. Now, a couple things here. First, you got to pick out which reaction you want to use. You can use whichever one you want. We have NH4 plus, okay, plus H2O yields NH3 plus H3O plus. They're both present. Initial stoichiometric ratio N. Now, one thing I might note, because we're adding 2 separate volumes, the new concentration of this guy, we double the volume. 0.1 doubles the volume to 0.05 molar and 0.05 molar. I could have used the acid version or the base version. It just doesn't matter. I kind of like this one better because I get a H plus ion, which means I go directly to pH. Okay, not playing a role. Minus X plus X plus X. Doesn't even matter which way I'm going. I can just put the numbers in like this, and it's 0.05 minus X, 0.05 plus X, and X. Okay, my Ka equals, in this case, I'm going to use my shortcut rule here, 0.05 times X, that's this guy, over 0.05. My Kb for this reaction was this guy, 5.6 e to the negative 10th. Okay, so 5.6 e to the negative 10th equals, now this is going to cancel here, equals X, so it's nothing left. Now, this is a little shortcut rule here, that what happens if your acid and your base are equal concentrations? It's got a special name called the, even though they're equal, it's called the 1/2 equivalence, and we will see that in a moment, kind of why that is. But either way, it's coming up in titrations. At this point, this is the concentration of the molarity of your H plus ions, and you would at that point just take the negative log of this, and which is equal to, let's run this. All right. Negative log of 5.6 e to the negative 10th equals 9.25. Okay, so notice that negative log of that value equals, I'm going to show that work-wise, that you're taking this in there, equals 9.2. So we are basic. And why are we basic? Well, we're mixing two things together. Equal concentrations, okay, equal volumes. All right, so, but this guy's much stronger, which means it's still going to be basic. What's that mean? It means that even though we have equal concentrations of these things, the NH4 plus is not efficient at rolling basically breaking these open, kicking them this way. So it's not very good at actually using them. There's just as many there. It's just a little bit less effective at actually using them. That's it. I'll put this on here, and we'll have at least, this is just one example. This is your main example of what you do when you have 2 weeks. Okay, and we'll stop there. Thank you very much.